Up next, we have the thyroid gland. And the thyroid gland, we'll discuss first the anatomy, and then we'll talk about why the thyroid is really important in processing thyroid hormone and what does thyroid hormone eventually do for us. So first, starting with the anatomy, we have a thyroid gland, and it sits, let's see if I actually have a picture from one of the beginning slides. It sits just anterior to your trachea. Let's see right here. Yep, this is a nice picture of it. So here we can see right here in the cervical region, we can see that thyroid gland sitting right inferior to the thyroid cartilage, right inferior to the hyoid bone and just anterior to the trachea. And it kind of looks like this butterfly structure like this. And right in the middle of that, we're going to call that an isthmus. Right here at the middle is an isthmus. So if you are familiar with geography, an isthmus is like a narrow strip of land that connects two other lands together. So that's why this is called an isthmus. And the size of a thyroid gland varies from individual to individual. So as a child, they might be relatively normal size. And then in adulthood, they might get much bigger or much smaller, depending on what's going on. And again, you don't want anything too big or too small, otherwise that's going to be an unhealthy balance. Or maybe there's some sort of cancerous tumor or tumor growing in that gland. But the average size across the board is about 34 grams. Within the thyroid gland, you'll have thyroid follicles, and these thyroid follicles are units of the thyroid that are going to be producing thyroid hormone. Within the thyroid follicle, you'll have a follicle cavity, and in the follicle cavity, that space is going to be sitting some sort of gelatinous liquid called a colloid. And surrounding the thyroid follicle, we have something called clear cells or C cells. And the C cells are actually what's making calcitonin, which is important for balancing calcium levels in the bloodstream. And in the colloid, we're going to have some important enzymes in there as well, which we'll talk about whenever we draw out this process. And what we need to understand is that there are a lot of different pieces to this structure. So if we have the thyroid cavity, right, within the cavity, we're going to have the colloid. And surrounding the cavity, we'll have the rest of the thyroid follicle, so those supporting cells. And within those supporting cells, we'll have some occasional C cells. Okay, so the question might be, what is in this space? That would be the colloid. Or the question might be, name the space? That would be the thyroid cavity. Okay. So next we need to talk about how the thyroid gland actually makes thyroid hormone. And so this is the picture that your book gives you, and it goes through step by step of what's going on. And I've drawn a similar picture here on the right. So on the top half of this picture, we have the colloid in the follicle cavity, which I have here in yellow on the right-hand side. And then the bottom, we have the blood capillary, which I also have here on the right-hand side as a blood vessel. So feel free to use the book's rendition of this if you'd like, or feel free to use this picture, whichever feels more comfortable or easy to you or easiest to understand. So we'll go ahead and start with an iodide ion. This is a terrible picture of a person, so I apologize. Iodide. And we're going to ingest this. Okay, let's talk a little bit about what iodide is. So iodide used to not be found in a lot of our regular food supply. And in the early 1900s, I believe, people started going to the doctor with lots of thyroid-related issues. Either they had hypothyroidism, so their metabolism was really low. They weren't able to manage their heat production very well. They weren't able to manage their metabolism very well. And so the industry was like, all right, how do we get more iodide into people's diet? So they added it to table salt. So this is why whenever you go to the grocery store, you might see salt with or without iodine. Now we have enough iodine in the rest of our food that we don't really need to add it to the salt, but unless your physician says otherwise, I wouldn't worry about it. Okay, so we eat it, right? And then once we eat it, we digest it and we break it apart, and then we finally get it into the bloodstream. And once it gets into the bloodstream, then it finally goes into the tissues. And once it finally goes to the tissues, it's going to find the right tissue, which is going to be the thyroid gland. And once it gets into the thyroid gland, then it's going to enter the thyroid follicle. So that's our general process. Okay, so now let's kind of draw that out here with some added steps. So we start with iodide floating around in the blood, right? Then it's going to enter into the thyroid follicle, and there it's going to be converted into iodine. Let's just call that chemistry. I wouldn't worry about the Y's. Okay. Then at the same time in the thyroid follicle, we're going to be having something called thyroglobulin, which I'm going to abbreviate TG, being recycled. And both thyroglobulin and iodine are going to then go into the thyroid cavity, into the colloid. And thyroglobulin is a nice protein, and it's very good at holding on to iodine. So in the colloid, they will come together, and iodine will add itself onto 4 binding spots on the thyroglobulin. It can actually do one of 2 things. Sorry, it can either hold on 4 different spots, or it can hold on in 3 different spots. Either or. Okay. And so now at this point, since it's with 3 or with 4, we can actually call this thyroid hormone. And we'll abbreviate T3 since there's 3 iodines here, or T4 since there's 4 iodines there. Okay, so now we've made thyroid hormone. Now we need to get it back into the bloodstream so it can actually do what it needs to do. And so at the colloid, we'll have the colloid exocytose this thyroid hormone. So I'm just going to kind of draw it like this, like it's going to exocytose and squeegee its way out back into the follicle. So T3 and T4 get exocytosed into the follicle. And in the follicle, we have some lysozymes waiting for it. And if you remember, lysozymes are vesicles filled with enzymes that are able to digest and break apart things. So these lysozymes are actually going to take T3 and T4 and break it apart so that we can carry around just the 4 iodine molecules or just the 3 iodine molecules and recycle thyroglobulin so it can make thyroid hormone again. So let's go ahead and draw that out. So lysozymes are going to break it apart into thyroglobulin and just the 3 iodine molecules and just the 4 iodine molecules. So this thyroglobulin can then be recycled and used again. And then the hormone, T3 and T4, can then exit its way back into the bloodstream. Okay. All right, well, now that's awesome. Now it's in the bloodstream, but then what? So actually T3 by itself is actually the active form of the thyroid hormone. So it can float around in the bloodstream and do whatever thyroid hormone needs to do. But T4 is not the active form of it, and instead it's going to be bound to some carrier proteins so it can float around in the bloodstream until it needs to be activated. And we actually have a specific example of these carrier proteins, that being albumin. Okay, so albumin is going to bind to T4, carry it around, and convert it to T3, the active form of thyroid hormone, whenever we need it. That's it. Relatively simple. Okay, so now what we need to think about is kind of what's happening for when we would need T3 or T4, right? And how we could affect the homeostasis of it and encourage the hypothalamus, anterior pituitary, and thyroid gland to produce their relative hormones. So so the way to read these pictures in your book, one side is going to be like or one side will always be the imbalance and the other side will also be the other imbalance, and they're supposed to like teeter-totter to each other. So the on the left-hand side, we have homeostasis is disturbed by not having enough T3 or T4. And so then the hypothalamus registers that, releases TRH to the anterior pituitary then releases TSH, and then that goes to the thyroid gland, and then the thyroid gland tells the thyroid follicles to make T3 and T4, and then we restore that homeostasis by increasing the levels of T3 and T4. So now let's think about what would happen if we put the normal person through a couple different scenarios. So what if the person didn't have any iodine in their body? They didn't ingest any of it. What would happen to T3 and T4 levels? Would they increase or would they decrease? Well, they would decrease because we need iodine to make T3 and T4 to begin with. So if we don't have any of that, we won't be able to make T3 and T4. And if we don't make enough T3 or T4, the hypothalamus is going to go, oh my gosh, we don't have enough T3, T4. We need to make more T3, T4. So then the rate of TRH and TSH production is going to increase dramatically. What if we don't have any TSH? So this is being released from the anterior lobe. Well, then again, we're not going to have the thyroid gland making T3 and T4. And whenever we don't have enough T3, T4, then the hypothalamus is going to make more TRH to tell the anterior pituitary to make more TSH. And then that'll be it, because we don't, we'll just have increase of TRH, but the anterior lobe is just not responding to it for whatever reason. So we're not making any TSH, and we just kind of get stuck there. What if we have too much TSH? If we have too much TSH, right, that's saying that the anterior lobe is making too much TSH, which means the thyroid gland is probably making too much T3, T4. And that's going to tell the hypothalamus, hey, we can just kind of chill out. We don't need to do that anymore. So it'll decrease the amount of TRH it's releasing. But maybe that's not sufficient enough. Maybe there's some sort of tumor in the anterior lobe that's making more TSH than normal. And so if we have a bunch of thyroid hormone floating around in the bloodstream, then we're going to have a hyperthyroid disorder of some sort. We might not be able to stop it. And this is all just kind of examples of what would happen for each of these scenarios, but it's a good way of thinking about the normal process of the thyroid gland. Okay, now last but not least, too little TSH. So if the anterior lobe, for whatever reason, is not able to make TSH, but we still have a little bit of TSH, then we're still making some T3, T4, but the hypothalamus is still going to be like, hey, we need to make more. So then the hypothalamus is going to keep releasing more and more TRH, but maybe the anterior pituitary just doesn't respond regardless. So we're just going to be in a hypothyroid state because we're not going to have enough thyroid hormone. So what does thyroid hormone do? Thyroid hormone can bind to cytoplasmic receptors for storage in the cell. That should tell you something about if it's a peptide hormone or a steroid hormone. That means that it's going to be a steroid hormone. It can also bind to the mitochondria to increase ATP production, which we also saw for steroid hormones. And then finally, it can also bind to the nucleus to make more sodium-potassium ATPase channels, which are going to help exchange sodium for potassium at various different cells in the body, which is a really important function for many cell pathways. In general, the thyroid hormone usually increases metabolism and increases generating heat and increases using calories or using energy stores to make more ATP and then burn that ATP. Like I said, those C cells are making calcitonin, and so what does calcitonin do? Calcitonin is going to work with the parathyroid hormone, which is released from the parathyroid gland, which is just on the posterior aspect of the thyroid, which we'll talk about in the next section. And calcitonin is going to be counteracting what parathyroid hormone is trying to do. So calcitonin, I always remember bone in, calcitonin. So it is trying to increase the calcium levels in the bloodstream. Let me make sure I said that correctly. Stimulate. Correct. Yep. So we're increasing more calcium deposition into the bloodstream. And in order to do this, calcitonin is going to go to the bones and tell the bones to release more calcium. And it'll also tell the kidneys to not hold on to calcium as much so that the calcium can stay within the bloodstream and not go into the urine. And then whenever we have calcium in the bloodstream, then the idea is that we can use that for more cellular functions that we need calcium for. If we don't have enough calcium in the bloodstream, then parathyroid hormone is going to be released. Oh, hold on, I think I said this backwards. Calcium, bone in. So we're increasing, I'm sorry, I said this backwards. So we're increasing calcium into the bones. So it's being absorbed by the bones and being used to create more bone, or being used to help turn on osteoblasts to build bone. Versus parathyroid hormone is going to do the opposite. It's going to encourage more calcium to be deposited into the bloodstream. So let me write that out. So parathyroid hormone, more calcium in blood, and calcitonin, less calcium in blood, which means it's back into the bones. Okay. Next is the parathyroid gland, and I'll just talk about this briefly here. It's just one slide. So we just talked about parathyroid hormone and what's the purpose of parathyroid hormone. Now let's just talk about where the parathyroid gland is. So on the posterior aspect of the thyroid, which you can see in this picture here on the slide, those four little nodules on the back side of the thyroid gland, and each of those are parathyroid glands. You don't need to have all four to have normal production of parathyroid hormone. I believe you can live with just one. You don't even need to have all four. And in total, they weigh about 1.6 grams, so math, a very small proportion of the 36 grams on average of what the thyroid gland is. Parathyroid hormone will be released in tangent with calcitriol, and calcitriol, there's an L here, and then this L we could draw an arrow here, and that's going to be to increase the calcium in the blood. So when calcitriol is released, that's encouraging parathyroid hormone to be released to overall increase the amount of calcium we have in the blood. And the cells of the parathyroid gland we call principal cells. And those principal cells are the ones that are actually making parathyroid hormone. And we can see that here on the slide.